Saxon's Trig, Lesson 93, Advanced Trigonometric Identities and Triangle Inequalities for the second time. So we've been doing our trig identities where we take one side and prove it equals the other side, or we just manipulate to do whatever it wants. Now, in example 1, it is giving me 1 plus sine of b over cosine b equals cosine b over 1 minus sine b. So when I attempt to look at the first part and manipulate it and turn it into this part, well, that's like mess. So I can't even do anything with 1 plus sine. I could do something with 1 minus sine squared or sine squared minus 1. I can't do anything with this. So when this happens, instead of just looking at this part, I need to look at the entire problem. So if I can fraction equal fraction, cross multiply and prove that those two answers are the same, then I'm going to be good. So that's what we're going to do here. So this side times this side is going to FOIL out. 1 times 1 is 1. 1 times negative sign is negative sign, but this one, 1 plus sign, is going to cancel that off. Positive times negative is negative. Sine times sine is sine squared of b equals, now let's do this one, cosine times cosine is cosine squared of b. Oh, wait, is that one of those memorized? Beautiful, it's a memorized formula. I can check mark it. Example 2. Tangent b plus 1 over tangent b minus 1 equals secant b plus cosecant b all over secant b minus cosecant b. Does it look like this is something where I can nicely rearrange one side to the other? Maybe. I do know that I can go ahead and write my tangent as sine over cosine, so I can turn sine b over cosine b plus 1 over top of, repeat, sine b over cosine b minus 1. And then it would still equal my secant and cosecant information. Does doing that help me? I can create a common denominator of cosine b, but I'm not sure that's the right direction to go. So would writing sine b plus cosine b over cosine b help me? I'm going to keep going. Let's just explore this out. Cosine b, common denominator for the bottom again. I'm ignoring this side at said moment. So that would be, let me see if I can write it here. Sine b over, no, wait a minute, plus cosine b over cosine b over top of sine b minus cosine b over cosine b. And if I flip this fraction and put it up here, well, that's going to cancel off the cosine b's and give me sine b plus cosine b over sine b minus cosine b. And I'm still trying to make that equal to this. Oh, did that help me any? Not that I've seen so far. All right, secant is the opposite of cosine. So maybe if I make this 1 over cosine b, and cosecant is the opposite of sine, so 1 over sine b over, do the same thing again, 1 over cosine b minus 1 over sine b. Well, now I've gotten everything to sines and cosines. Common denominator and flip to put them together just like I did before. That would give me, let's see, 1 over cosine b plus sine b flipped with cosine b minus sine b over 1 when I'm multiplying it. So that's going to give me I'm going to rewrite this one. Sine B plus cosine B over sine B minus cosine B equals cosine B minus sine B over cosine B plus sine B. Okay. They're not identical. The signs have been flip-flopped. If I do a cross multiply at this point, I can be getting, I'm debating whether I want to FOIL it or write it with parentheses. Just a second. Before I finish my lovely thought process, they have done it a very different way. There are multiple ways to do different things, but they're not matching me at all. Okay. Sine B plus cosine B, I'm cross multiplying, with cosine B plus sine B, oh, that's like saying it's squared, not over top of, should equal the other side, which would be sine B minus cosine B, multiplying with cosine B minus sine B. Ooh, I do see that like this one's a positive sign, this one's a negative sign. So it's not an actual squared, whereas this one, the order doesn't matter, and they're both the same in essence, so they are squared. At this point, I think I would have to FOIL it out. I hope we're not going through all of this work only to discover it doesn't help, and I have to go back to the other way. All right, so sine B, cosine B, sine B with sine B is a sine squared B, plus cosine times cosine, cosine squared B, and now my last, cosine B times sine B equals, now I do see that my sine squared plus cosine squared is a 1. And these are identical. So technically I can be saying 2 sine B cosine B equals sine B cosine B minus sine squared B minus cosine squared B plus cosine B sine B. Okay, that's distributed. So sine and cosine, sine and cosine. So that's 2 of those. 2 sine B cosine B's. Okay, I'm not trying to prove that it equals anything. I'm trying to prove that they are the same. And I still haven't dealt with this minus sine squared minus cosine squared. But since that equals 1, not 0, I can't just change those signs. Oh, hold. I was really close to having it. Okay. So I failed to write the 1 plus here. I put those two together and didn't write this 1. And I still have to write over here the minus sine squared B minus cosine squared B. And I said that these two were the same, so I knew I could, whichever one I moved to the other side, cancel off the other. So what do I have at this point? 1 equals negative sine squared B minus cosine squared B. And this is where I was debating. I know that the fact of sine squared plus cosine squared equals 1. So I'm debating if I dorked a sign somewhere in my work, and this should have come out sine squared plus cosine squared equals 1. And it's possible that that's what I did. Since it's that close, I feel like maybe if I go back, I could find where I had a sign that was not right. But it should be marking off as coming out with positive signs sine squared plus cosine squared equals 1 because that's one of the memorized facts. Rather than taking the time to figure out where my negative went awry, this is one way that should work unless you've made an error, but there's so many places to have made a mistake. They did it very differently by actually multiplying both sides by 1 over sine and doing some reducing. And their way looks a little easier than chunking through mine. So let's leave example 2, move on to example 3. It says to show that x sine of theta plus y cosine of theta, and all of that squared, plus x cosine of theta minus y sine of theta is also squared, and that it equals x squared plus y squared. Okay. My squared means I need to FOIL it out. So x and sine theta times itself becomes x squared sine squared theta. This with this becomes x and y with sine of theta and cosine of theta, and there are 2 of them, double up the middle, plus, and this part becomes y squared cosine squared theta, and repeat, plus, and I'm going to run out of room, x squared cosine squared theta. Okay, this times a negative, so negative 2 x y cosine theta sine theta, and negative times negative makes positive y squared sine squared theta. Okay, so now we FOILed it all out. And I have a feeling if I manipulate this, I can make it go to this rather than using it. And I certainly can't do like a cross multiply because I don't have proportions. It's not fractions. So let's see. Positive 2 xy sine cosine minus 2 xy sine cosine. They're going to cancel off. Okay. Leaving me an x squared with sine squared, an x squared with cosine squared. So what happens if I pull the x squareds out? That leaves me sine squared theta, and here leaves me plus cosine squared theta. Now let's see if I can do the same with the y squared terms, plus y squared, and pull out. This one leaves cosine squared theta plus sine squared theta. Now each of these sine squared plus cosine squareds is 1. So 1 times x squared is x squared plus 1 times y squared is y squared. Hallelujah, that one was so much easier than the one before. Okay, part B is triangle inequalities. For the second time, we are going to discuss them. So we know that in a right triangle, our a squared plus our b squared equals our c squared. But for inequalities, we're not dealing with an equal. So the question here becomes, if I have a squared plus b squared, and it's greater than c squared, what's it look like? If I have a squared plus b squared, and it's less than c squared, what does that look like? Okay, so when this stuff is less than the c squared, it feels the opposite because these two sides are being told that they are less than the other one. But the triangle that is formed is the obtuse triangle. When the two sides added and they are more than the hypotenuse, then it is an acute triangle. It just feels backwards, but that's the way they are. So I would jot those down in my notes to have them. And then what the book is going to ask is, oh, I'm ignoring their kind of proof of that, and I'm jumping to their example. Is the triangle whose sides are 3, 4, and 5 a right triangle, an acute triangle, or an obtuse triangle? So we're going to take the two smallest always, And the largest one will act as the hypotenuse, whether it is or not. I can't actually say it is because more than likely it's going to be acute or obtuse. But 3 squared is 9, 4 squared is 16. How does that compare with 5 squared, which is 25? So this is 25 is the same as 25. So this one is actually a right triangle, so that 5 was my hypotenuse. In example 5, it says, classify the triangle whose sides are 4, 7, and 5. So the largest one is the 7. 4 squared is 16. 5 squared is 25. How does that compare with 7 squared, which is 49? So 41 is comparing to 49. The two together are less than the other, so the two adding up are less than the other. Therefore, it is an obtuse triangle. Now, before I close this, let me see if I want to definitely skip how they were showing it. It's based on Pythagorean theorem. Yeah, it's manipulating, based on Pythagorean theorem and manipulating with algebraic steps. And instead of the equal sign, they're substituting in the greater than or less than. If you wish to look through that other part there, you are welcome to do so. I feel like it's fairly straightforward and nothing complicated, and I'm going to stop it at that.